This is Mr. Anderson for Kellogg Community College. We are going to be looking at Section 2 of Chapter 9, Exponential Functions. Now the equation f of x is equal to a times b of x. A is going to be the start value, or the seed as some might call it, and the b is going to be our rate of growth, or our rate of decay. So the exponential growth is when the b value, or the number, the base of the exponent x, is going to be greater than 1. So if we are doubling something, the b is going to be 2, and if we're tripling something, the b is going to be equal to 3. Exponential decay is when the b is between 1 and 0, or it's a fraction, decimal, or a percent. Because what this does is it gets rid of a certain percentage of that graph at the same time. Exponential growth graphs look like this, and exponential decay graphs look like this. So the domain of the b value for my problem should be greater than 0. So if b is greater than 1, it's going to be exponential growth, and if b is between 0 and 1, it's exponential decay. Through this worksheet, we're going to be dealing with different pictures of these, and we'll graph them onto the screen. I will show you how they look on the graphing calculator, and also do a little plot to the right here. Okay, so the first thing we're going to do is type in y to the y equals 5x. So turn my calculator on and go to my y1 and clear that out. And I'm going to go y equals 5 caret x. This is going to be an exponential growth problem. The exponential growth problem will also look like this. And the best way to graph this is to look at our table and to get 5 points. Now, since these points go off very, very quickly, I like to choose 2 points from 2 points like -2, -1. Pick the point 0, obviously, and then pick the points 1 and 2. So let's go graph these. -2 and 0.04, or 4 hundredths, is very small, so it would be very close to the bottom there. -1 and 0.2, which is about 20%, that's going to be about quarter of the way up. At 0, it's 1. At 1, it's 5. And at 2, it's 25. Now, since I'm graphing off the grid there, I'm going to choose another point, like let's say the -3 is 0.08. And since that's on the screen, I can easily graph that like so. So here is an exponential growth graph of y equals 5 to the x. All right, let's look at the next problem. This is going to be y equals 3 to the x, and then -1. This is going to be an exponential growth problem because of the 3, the number, or the letter b, being greater than 1, and this is going to shift the graph down 1 unit. So you see that it's shifted down 1 unit vertically from the original graph. Now, the reason why we didn't see that before is because here's the graph being drawn. Now, since there's an overlap, you wouldn't actually see, due to the size of the pixels, that line. But once we put the -1 on it, you can see that it is a shift down 1. Let's go look at the table here and pick some values. And we can only choose table values that go to 10 here. So it looks like I can choose -2, -1, 0, 1, and 2. So let's go take a look here. This is to graph problem number 2. So let's go put this up here at the top. Alright, so here we go. Let's go plot some points here. -2 is -0.89, so that's almost -1 there. Put that really near the bottom there. It's very close to the bottom. -1 is going to be 0.67, so about 2/3 below the line. 0 is 0. 1 is 2. And 2 is 8. So it does unfortunately go right to the edge of the screen here. So if I was to plot these 5 points, it would scroll up like this. Alright, let's do graph number 3. Alright, let's move this up here to the top. And I'll start using this graph down here below. Alright, so here we have y equals 2, so this is another growth graph. But in this case, since I need the x minus 1 to be the exponent, I'm going to use parentheses to enshroud that x minus 1. And what this will do is it will shift the graph 1 to the right. So this graph is shifted to the right because of the x minus 1. It would be shifted to the left, it would be x plus 1. So again, I'll show you an example of the graph with the shift, and here's the graph without the shift. This is 2 to the x. So here's the shift, here's the graph with the shift, here's the graph without the shift, so you can see that this x minus 1 does indeed shift it to the right. Alright, let's go to our graph then and take a look at what values they've given me. Looks like I can use 3 positive values here, actually 4 positive values. So I'm going to graph from 0 to 4, just because that's pretty easy. Alright, so graphing at 0 is going to be 0.5. So let me go put a dot at 0.5 at 0. 1 is 1. 2 is 2. 3 is 4. And 4 is 8. So if I'm going to connect my lines here, noticing that this does have a tail, that's how it looks. Alright, let's go to problem 4. Oops, lost my cursor here. Alright, so let's go to problem 4. Get the calc back up here. This is going to be 1/5 in parentheses to the x power. This is going to be a decay problem. It's going to be a decay problem because it's going to start from up above and then swoop down below. Let's go take a look at our table and see what values we can put on here. Well, -2 is going to give me a value that's too high, so I'm going to have to start with -1 as I graph this. So starting with -1 on my x-axis, let's go start plotting these points in. So -1 goes up to 5, 0 goes to 1, 1 goes to 0.2, and already I'm at the bottom here. 2 goes to 0.04, then 0.08. So you can see that very quickly this graph kind of drops off to something that we just can't see the negligible differences after we get past the first stage, or when x was equal to 1. Alright, problem number 5. Here I'm going to have to kind of like move to the right so we can see these problems. So this is going to be 2, and I'm going to change that to a plus just because I want to use another shift. I want to show you this, so future videos will probably, or future worksheets will probably have this as a plus. So if I go x, caret, I got to raise this to the power here, 2 raised to the x plus 3 power. Now will this be shifted 3 up, 3 down, 3 left, 3 right? And if you guessed 3 to the left, you would be correct, because the graph is shifted 3 to the left from where it normally is. So if I take a look at the graph without the shift, let's just type in 2 caret x, you can see the first graph was shifted 3 to the left from the original parent graph right here. So let's go back to here, let's clear this out. Alright, so now it's time to go to our table. So it looks like from our table here we've got some easy plots to pick. I can go from -4 to 0, it looks like. So let's go draw that on the screen. So -4 was 0.5. Whoops, get my pencil drawn right. -4 is 0.5. -3 is 1. -2 is 2. -1 is 4. And 0 is 8. There we go. There's your drawing. Alright, now things, we got to put the calculator away, because what's going to happen for, well, we don't have to put it completely away, but what's going to happen for problems 6 and 7 is that you'll notice that the equations don't have y equals, they're x equals. So what I need to do in these situations is I need to plug in some values into my y to see what it makes for x. So I'm going to draw this temporarily. It is going to go away. But what I'm going to do is for 6 and 7 is I'm going to make a table and focus just on my y values. I'm going to plug in maybe 2 negative and 2 positive values for my y to see what I get from them. And I'm going to do so on the calculator and then convert that into the table here. So let's go and show you what that would look like here on the calc. So what I'm going to do is type in, and then I'm going to have to graph this, of course, so that'll be kind of fun. Whoops, I keep losing my calc here. Oh, there we go. So here's what I'm going to do. I'm going to type in, let me see, that fits right there on the screen a little bit. Alright, so here's what I'm going to do, is I'm going to type in 2 caret negative, and then I'm going to try negative 2. This will be my first data point here, which gives me 4. Then 2 caret negative, and then negative 1. See, I'm just plugging numbers in for my y to figure out what my x is going to be, and it's going to be 2. 2 caret negative 0 is the same thing as 0, but I'll still, just to show you the pattern here, just plugging numbers in for my y there to see what gives my x, and that's going to be 4, 2, and 1. Now you might have to remember these because I'll scroll past them as I do the last two problems here. 4 caret negative 1 instead of negative 1, and that's going to give me 0.5, and then 2 caret negative 2, which is going to be 0.25. So this inverse graph, which I'm just drawn, this inverse graph is going to have 4 dots on it. Now let's go back and fill out that table, because what I did is plug in for my y negative 2, negative 1, 0, 1, and 2. And this gave me 4, 2, 1, 0.5, and 0.25. So 4 on my x was negative 2 on my y. 2 on my x was negative 1 on my y. 1 on my x was 0 on my y. And 0.5 on my x is 1 on my y. And 0.25 on my x is 2 on my y. So what we have here is this inverse graph that will never touch that y-axis, and will move on like this. So this is the inverse of the exponential of y equals 2 to the negative x power. So these are inverses of each other because I flipped the y's and x around, and this is where I substituted in the value for the y to find my x. So we're going to do the same thing for this problem down below. We're going to plug in numbers for my y, negative 2, negative 1, 0, 1, and 2, and go figure out what these are. Alright, so let's go process the problem here. Let's go to my screen draw, click that off. Okay, so let's go to a clear screen and type in 3/2 raised to the, let's go with negative 2 first. 0.444 or just 0.44. I'm going to make a side note of this because this is going to get taken away as soon as I do it. As I do enough of these problems, they're going to come off the screen. And let's see here, negative 1 is going to be 0.67. And then if I raise this to the 0 power, anything to the 0 power is going to be 1. So that's going to make 0 is going to be 1. And then we're going to do the same thing for the next set. We're going to raise this to the first power, so that's going to be 1.5 or 3/2, but it's easier to graph decimals than there is to graph fractions. And then we're going to go to 3/2 to the second power, which I believe is 9/4, which takes it to 2.25. So I'm going to now go back to drawing on the screen here so I can graph these points. So again, what we did is we took our y values, negative 2, negative 1, 0, 1, and 2, and plugged them into our x's. So this gives me 0.44, this gives me 0.67, this is 1, anything to the 0 power is 1, and then what we have is 1.5 and 2.25. So let's see how this works here. It looks like I've got 0.44 on my x is negative 2 on my y. 0.67 on my x is going to be at negative 1. 1 on my x is 0 on my y. Let's see here, my 1.5 on my x is 1 on my y, and 2.25 on my x is 2 on my y. So here's what I've got. Check out this inverse graph right there. And that inverse graph is the inverse of y equals 3/2 raised to the x. So you can see that these two graphs would be inverses of each other and be symmetric, like we learned in the previous section. Now our last piece of this worksheet is going to be looking at the story problems. And the story problems are actually pretty good, because what you have is some very straightforward plugging and chugging, but I do want to talk a little bit about graphing these. So what I'm going to do is show you how to estimate the percentages, but let's just talk about the problem itself here. The percentage of smokers, P, who receive telephone counseling to quit smoking and are still successful after 2 months can be approximated by this problem. What this is saying is that we're starting out with an average of 21.4 smokers. Now, the reason why this is not a whole number is because when you deal with different classes and different groups, your average isn't going to be always a whole number, because all the different sample sizes are going to create a situation where you're going to have an average that's a decimal. Now this is the success rate. Now you'll notice that this is decay because our B value is between 0 and 1. And a number between 0 and 1 is 0.91. What this means is that there's a 9%, approximately 9% or 8.6% failure rate in this group. So not 100% are sticking with the idea to quit smoking. So let's do an estimate of the percentage of smokers who are receiving phone call counseling who are successful for quitting in 1 month, 3 months, and 1 year. Alright, so for this, what we're going to do is type into the calculator, we're going to try P of 1 month, which is going to be 21.4 times 0.914 raised to the first power. Now if you type this into the calculator, which I'm going to do off screen, and that will give you an answer that's approximately 19.56 people. So if you start off with 21.4 people, you're going to have roughly 19.56 people, or closer to 20 people, still after the first month. In 3 months, you're going to type in your 21.4 and your 0.914 raised to the third power. And what this does is it will show you that after 3 months, you're only going to have 16.34. Sorry that I wrote that weird. 16.34 people left. So in this situation, you're going to see that after 3 months, you're still losing people. Now, remember, this is a failure rate of only about 9%. So how many people do you think will be left after a full year of this kind of problem here? And you're going to find that the failure rate is pretty bad. Like after a full month, there's only going to be approximately, again, wavy equal signs to show that these are approximate answers here. This is going to be 7.27 people. So you can see that with just a 9% failure rate, this is still pretty bad. That's still not a very good success rate. Now, the other way to do the problem is to go get your calculator, and you could have typed this into your Y1. You could have went 21.4 times a parenthesis of 0.914 raised to the x power, and you could have gotten all of these answers by going to your table, and you would have seen that you, after 1 month, would have had 94.56, and then so on and so forth, all the way down to the 12th month, which was about 7.27. Now it says graph the function on separate paper. Now what I would do is use this table as kind of your guide. I would start always with your 0. So this is going to be, I'm going to put this over here and graph this on the screen. So what I would do is when you do your graph is maybe think to yourself like, okay, what's reasonable here? What's reasonable is probably starting off around 20, even though the highest point is 21.4, so maybe 25, and go by fives. This is 20, this is 15, this is 10, this is 5, and this is 0. Now again, you'll probably make this a little bit better for yourself, so use a ruler and use some charts here. And you can go, as far as you really want to go. Again, once people see the general pattern here, they're going to see that, maybe going to 6 will be nice because I've got all of these on the screen. So 0 is going to be at 21 or so. 1 is going to be around 19, so it's going to be there. 2 is going to be 17. 3 is going to be 16. So this is really starting to taper off here, but you'll find out that this is going to get kind of dangerously close to 0 when we get to the very end. There's 13 and there's 12. So this does, the people who are dropping off of this, who are still able to stay non-smoking, is going to get closer and closer to 0 the further this goes on. So there's hopefully some better intervention out of there than phone counseling. All right, so let's go to the next problem, which talks about another decay rate. This is going to be half of all aluminum cans will be recycled each year. So let's see how that holds up over time. Now you'll notice that it's just going to ask how much after 0, 1, 4, and 10. Now in the previous problem, I just plugged the 0, 1, 4, and 10 into the little letter t here. But I'm going to save myself some time by typing in my 250,000 here, multiplied by my half, or 0.5, raised to the x power. Now if I go to my table here, I can see after 0 years, of course it'll be 250,000. But then as it goes on, after 1 year, there's only 120 of those original 250,000 cans. Only 125,000 are recycled. Then after 4 years, it dwindles down to about 15,000 cans, and then at 10 years there's only about 244 of the original 250,000 cans that are still being recycled. It's good, it's not great, but again, I think this data, I'm not sure what is actually realistic. I'm not sure if the book was getting this from a verified source. So now I'm going to graph this. Now it's best to use, again, I'm going to graph it from like 0 through 6 points. And I'm going to show you that the half-life, instead of a failure rate of 9%, a failure rate of 50%, is going to go down much more steep. So I'm going to start off with 250K, and to kind of like limit my lettering there, 250K. So these are all going to be 50,000s again. So 200K, 150K, 100K, and then finally 50K down here. And again, plot as far as you think you need to go. I'm going to go as far as this makes sense. So 0 is going to be at 250,000. 1 is going to be at 125,000, so you see it drops halfway. Then 2 is going to be 65 or 62,500, which again is dropping this half the distance there. 3 is going to be 30,000, so we're already now under the 50,000 mark. 4 is going to be 15 grand, and so you can see that this is going to quickly go to a spot where I'm going to need to magnify quite a bit, and that's where the table is kind of important. So if we analyze this graph versus the previous one, you would see that the 9% drop rate was a lot slower than this 50% drop rate. All right, so what we're going to do here is, and now most banks will not compound annually. They'll compound either continuously or monthly, depending on the terms of your bank or credit union. So what I want to do here is a very simple problem where we're going to find out how much we've made after we enter the principal amount. This is the principal. It's how much we have to invest, times 1 plus the percentage. Okay, here's our percent right there, for t, which is time years. So this is going to be A equals 1,000 times 1 plus 7% times the t, which is 5. Now 1 plus 7% is 1.07 because percentages are written as decimals. So A is equal to 1,000 times 1.07. And what I'm going to do is now multiply on my calculator 1.07 times 1,000 raised to the 5th power, and this will give me an answer of we'll have in our total amount $1,402.55. So it says in what year will the most money interest be earned, and why? Well, that's pretty easy. It would be between the 4th and 5th year, because you can see that we can kind of break this down and see at the at the start we'd be at $1,000. So this would be at 0. So at $1,000 at 0, and then in the first year I'd have $1,070. Then in the second year I'd have $1,144.90. In the third year, I'd have I'm just looking at all of these, $1,225.04. So there's my third year. Now I'm going to go to my fourth year, and my fourth year is $1,310.80, and I'm making the most jump between the fourth and fifth year, because every single year I'm earning interest upon the previous year's interest. So even though, to the naked eye this is going to look flat, over the long haul this is going to be an exponential growth. So maybe at 50, 60, 70 years you're going to see a big difference between the year and the previous year. So invest for the future, folks. Save for your retirement. All right, well, thanks for watching.